In the previous video, we discussed the derivation of a second-order differential equation based upon a dynamic systems example of an electromechanical shaker. Now, a speaker can also be considered an electromechanical shaker. The way this system works is you have a mass attached to a spring and damper, which are attached to a coil and a permanent magnet. The magnet induces current in the coil, which provides electrical energy to the mass spring damper system, and this is what allows the table to move and vibrate for the function of the electromechanical shaker. In this video, we will go further in depth into the derivation of second and third order differential equations and what they mean, also to further show where differential equations come from. And we will also show transfer function derivation once the second and third order differential equations are derived. And we'll also talk about the function and the meaning of transfer functions. Once we cover that, we will also talk about some applications of frequency response, which is what a transfer function allows you to see, as well as some cool real-life examples of this happening in real time. To begin, we will go over the second order differential equation derivation, looking at the mass spring damper system with the coil. The second order differential equation derivation results when current is considered the input. We will begin by going further in depth into showing the derivation of a second order differential equation. To begin, we will use a bond graph, and as we discussed in the previous video, a bond graph is used to show the power flow throughout a system, and this is broken down into efforts and flows. So on each power bond, you have flows on the bottom and efforts on top. In this case, our input flow is current, and our voltage within the electrical system is represented by VA. The current goes through a gyrator with a gyrator constant R, and this converts the current into the electromotive force, which is applied onto the mass spring damper system. This is how the electrical current exerts force onto the table. Next, we have a one junction which shows a common flow. In this case, our common flow will be the velocity of the table represented by Vt, and this is the velocity at which the table moves after it is excited by the current. Next, the next power bond is to show the first state equation of the system, which will be the momentum of the table. And once again, as also previously discussed, a state just represents a physical property of the system. So the physical property of mass in this case would be momentum. The next power bond on the one junction shows the power that is delivered to the spring system, represented by spring constant Ks. The second state variable is the spring displacement, represented as Xs, and the flow for this part, which is actually the same as the velocity of the table, is the velocity of the spring displacement, represented by X dot S. The final power bond for this one junction shows the power that is delivered to the damper, represented by damping constant Bs. Once again, we have the same velocity, which is exerted on the table, and the spring and the damper. So the mass spring and damper share the same velocity Vt as what is shown in this bond graph. And of course, we also have a force exerted on the damper. So what this one junction shows us is that you have a common velocity between the table, the spring, and the damper, and the electromotive force that is exerted by the current onto the mass spring damper system is shared between the mass in the form of momentum, the force on the spring, and the force on the damper. Once again, the two state variables for the system are the momentum of the table and the displacement of the spring, shown below as well. And finally, as a final note, we can also see that the velocity of the table will go back through the gyrator to be converted back into a voltage, which is a back EMF exerted onto the coil and magnet system. Back EMF tends to exist in dynamic systems where you have an electrical component involved. Lastly, we can see the equations relating electromotive force to the current, and also the back EMF voltage related to the velocity of the table. And as is seen from this bond graph, the electromotive force is split off into the rate of change of the momentum, the spring force, and the damper force. And remember, rate of change of momentum is mass times the rate of change of velocity, because momentum is mass times velocity. And P dot, rate of change of momentum, is what allows you to convert this term into a force. So to begin the equation derivation, we will just show some basic equations that are related to the system. So velocity on the table is related to momentum, and momentum is mass times velocity, or mass times x dot, which is the rate of change of the spring position, which also equals the velocity of the table. The electromotive force related to current, the damper force, and the spring force. So the sum of forces is mass times acceleration, which is mass times the rate of change of velocity. So that equals P dot, which is the electromotive force minus the damper force minus the spring force. And then we continue, we can show P dot in terms of the state variables, momentum and spring displacement. And we can show how each of the expressions on the right were substituted into this P dot equation. Next up, to show our second state variable, we have x dot s equaling to the velocity of the table as we saw in our bond graph. Finally, in order to derive the second order differential equation, we simply take the second derivative of x dot s to make x double dot s, which is related to 1 over the mass times p dot. And as we notice from the first equation, p dot is the first equation that we got from the sum of forces, and that can be substituted into the x double dot equation. And the momentum in the first equation can also be shown as mx dot, which will result in an x double dot term, an x dot term, and a regular x term to show our second order differential equation presented here on the bottom. So what this equation represents is the displacement of the spring, the velocity of the spring, and the acceleration of the spring, which also would represent the position, the velocity, and the acceleration of the table itself. And this is all equal to the input, which is the current input. Once we have this second order differential equation derived and written nice and concisely, we can now use this equation to show what the damping coefficient of the system is, as well as the system's natural frequency. So the damping coefficient, or the damping ratio, is represented by the coefficient attached to the x dot term, which is Bs over mt, the damping constant divided by the mass of the table. And 2 zeta omega n represents 2 times zeta, the damping ratio, and omega n, the natural frequency. And secondly, the natural frequency is omega n squared, which is equal to the spring constant divided by the mass of the table. Once you find the natural frequency using a given spring constant and mass, you can go ahead and find zeta as well. Now, to get an idea of what natural frequency is, picture this. In this video, you can see that the kid screamed at just the right frequency in order to shatter the glass. The reason that the glass shattered is because he happened to scream at the glass's natural frequency. When you emit sound waves that are close to or equal to the natural frequency of an object, that object will rattle itself apart and be destroyed. Every object in the world has a different natural frequency. Dynamic systems is one way in which we can figure out what the natural frequency of objects is based on different properties of the system.
Looking at it directly down the bridge itself, and that simply it begins to break apart.
Next, we will go over the third order differential equation, derivation, and this is found by using input voltage as the input instead of current. Now, if we look at our system again, previously we stated that the coil had current induced in it by the north and south poles of the magnet, and input current was supplied to the system. However, if you use input voltage, that means that you need to rely on a resistor and an inductor, namely the inductor, to get input current. So now lambda, which is flux linkage and related to the inductor and the induced current, will now become the state. So we introduce a third state to this system, which is lambda, and this third state will cause a third order differential equation to result. So the bond graph for this will look a little bit different. So we start with Vn being the input effort source, and we will go directly to a one junction, which will be representative of the current, the common current flowing through the resistor and the inductor in this coil parameter part of the dynamic system. So once input voltage is applied, the next power bond will represent the inductance that results in the system and the current that the inductor induces into the system. So a voltage is applied to the inductor responds by inducing current back into the system, hence the one junction. Next, we have the derivative of flux linkage, which is lambda dot A, and this represents the inductance, which is L, multiplied by the derivative of the current, which would be IA. And flux linkage is analogous to momentum because momentum is mass times velocity for a certain mass. Flux linkage would be like the electrical momentum, in that flux linkage would be momentum, and then inductance would be like mass, and current would be like velocity. So you could call flux linkage the momentum of an electrical system. Next, we have also power flowing to the resistor, which is represented by a resistance RC, and the same current that the inductor induces in the system is also applied to the resistor, and the resistor has its own voltage. And something to take note of here is that lambda dot is analogous to voltage in the same way that P dot, or derivative of momentum, is analogous to force. Once we have this induced current IA from the electrical system, we once again use a gyrator to convert that current into the electromotive force, which is exerted onto the mass spring damper system, which is analogous to the second order version of this bond graph. And once again, we also have velocity of the table, which is represented by the one junction to show the mass spring damper system. And this part of the bond graph is exactly the same as for the second order system. Once again, we can now see that lambda is the third state. So lambda, momentum, and spring displacement are the three states of this system. As previously, the current, which is now induced by the inductor instead of just applied as an input, is converted into electromotive force. And then the resulting velocity on the table is converted into the back EMF represented by VA. And this back EMF is exerted back onto the coil and magnet system. And the equations relating the electromotive force to the current and the back EMF to the induced velocity are shown below by using R, the gyrator constant. A gyrator converts electrical energy into mechanical energy and then mechanical energy back to electrical energy in this case. As was shown in the bond graph for the first one junction on the left, we have a sum of voltages, which is lambda dot A equals to the input voltage minus the voltage on the resistor and minus the voltage that is applied through the gyrator. And on the right, we have the general equations that represent the voltage on the resistor, the voltage that goes through the gyrator, and then as well as lambda, momentum, and the electromotive force. Next, we also have the sum of forces as in the previous equation, which allows us to find P dot. And here we begin to represent the three-state equation. So lambda dot in terms of state variables, P dot in terms of state variables as previously, and XS dot also in terms of state equations as for the previous second order equation and bond graph representation. So now with these three state equations, we also have an output equation which will be used for the transfer function later. The output in this case is to measure and show the acceleration of the table in response to this whole dynamic system. And this is also shown in terms of state variables. Now, once we have these three state equations, lambda dot, P dot, and X dot, we can convert these three equations into one large third order differential equation, which will show X triple dot, X double dot, X dot, and X, all representative of the table. So here we show different equations which are going to be used for all of the substitutions. So we start with P dot, and P double dot. P double dot is what will allow us to get the X triple dot part of the equation. And lambda A, which is another important part of this equation, is shown here in terms of P dot, which is mx double dot, and regular X and X dot. So we have lambda A as previously, and then momentum dot as previously, and X dot. Now we can begin some substitutions. So we take the second derivative of P, which results in this equation shown in white. And this is in terms of lambda dot A, P dot, and XS double dot. Next, we can show how P double dot equals MX triple dot. Now with a few more substitutions, namely P dot into the lambda A equation in green, and then P into the lambda dot equation, lambda A substituted into lambda dot, and lastly lambda dot A substituted into the P double dot equation. Finally, after a lot of algebraic substitution, you will have a nice and concise third order differential equation. And this is shown by representing X, X dot, X double dot, and X triple dot. This represents the position of the spring, which is also analogous to the position of the table, the velocity of the table, the acceleration of the table, and jerk, or change in acceleration of the table. To get an idea of what X triple dot is, or change in acceleration, or jerk, picture this scenario in which you are trying to get onto the highway by using an on-ramp, and then you see an 18-wheeler speeding in the lane that you're trying to get into, and this 18-wheeler is about to steamroll you, and the only choices you have are to floor your accelerator pedal,
Of course, guitarist Matt O'Brien is in some serious trouble. He's back Monday, police correspondent at his house, where it turns out was on fire.
to rapidly and aggressively accelerate, or to slam on the brakes and aggressively decelerate to prevent being steamrolled. Now, say that when you're on the on-ramp and you're accelerating at 2 miles per hour at steady state, that means your velocity is changing 2 miles per hour every second. And this is steady, so you're constantly gaining speed. Now, when you make your decision to either floor the accelerator pedal or slam on the brakes and have your rapid acceleration or deceleration, maybe now your acceleration changes by 5 or 6 miles per hour every second, as opposed to 2 miles per hour every second. And this can be felt by how your back gets pushed into the seat as you floor the accelerator pedal, or how your chest and stomach get pressed into the seatbelt as you slam on the brakes and rapidly decelerate. So that's hopefully an idea of what jerk is, and you can picture that in your head, a rapid change of acceleration from steady state acceleration. The next part of this will be to discuss the transfer function, but that will be done in the next video because this video is already getting pretty long. But hopefully you can appreciate the significance of differential equations, and hopefully if you've seen things like this before in a differential equations class, or perhaps in a dynamic systems class, you can actually see where these come from and everything that they represent to fully describe a dynamic system. So I hope you found this video helpful and useful, and hopefully you gained a newfound appreciation and understanding for differential equations. Because I certainly did in taking the controls class, from which I gained this knowledge, and in actually taking it upon myself to derive a third order differential equation, something I had never done before. So with that, stay curious, and I will see you in the next video.